So it's an absolute delight to be here to celebrate the achievements of WE. I do have silly pictures, but they come at the end, so you'll have to be patient. You have to stay, right? So I was a postdoc in WE's lab until very recently. I just started up at the University of Wisconsin-Madison. So nearly everything that I'll be talking about today was done while I was a member of the Merner lab. There'll be a little teaser at the end of some of the new stuff we're trying to do at Madison. I'm going to assume that over the break, everyone has forgotten all of the wonderful reasons to do single molecule measurements. So I'm going to remind you with two fairly ridiculous motivational analogies. I will, again, build the case for the use of this device for doing solution phase single molecule microscopy and spectroscopy. And then we'll be talking about applications of that device to two systems, a photosynthetic antenna protein called Allophycocyanin and an enzyme called Nitrite Reductase. So I think this is always a really important question to ask, and WE beat this into my brain over the course of my postdoc, and I'm really happy he did, because these experiments are tricky, and you really want to make sure you have a good reason for doing the single molecule measurement as opposed to the ensemble measurement. And so to illustrate my point, I'm going to use an arrow. And this is a magic arrow. This magic arrow represents any chemical property that I happen to be interested in. And the cool part about doing chemistry is that these properties tend to change as a function of time. So for example, this could refer to the some conformational state of a protein, maybe as it forms some cog, as some kind of a part of a grandiose signal transduction cascade. It might be the redox state of an enzyme. We'll talk about that a little bit later. It might be the electronic state of a protein. We'll talk about that also. But the problem is that when you do an ensemble measurement, this is what you get. I hope no one getting too dizzy right now. And when you try to and everything's unsynchronized. You know, one molecule doesn't know what the other molecule is doing. And when you try to make this measurement, right, this is what you see. And this is a perfect description of a dynamic chemical equilibrium, right? You have a round-bottom flask full of beautiful bonds breaking and bonds rupturing, but when you look at it, it's just a dull yellow the whole time. But if you try to make that measurement one molecule at a time, all those beautiful dynamics come rushing back. And this is why we do single molecule measurements. And if you want to build in some of the things that Callie said earlier, if you want to see arrows spinning at different speeds corresponding to heterogeneity, right, this is the technique to do it. All right, what about single molecule measurements in solution? Why is that interesting or important? And to build up this case, I'm going to ask the members of the audience to do something they're perhaps not used to doing. I'd like the analytical chemists to take a moment to empathize with their molecules. And so I say, what if I didn't want to do single molecule measurements? What if I wanted to do single chemist measurements? And I maintain that if you wanted to do single chemist spectroscopy, and this is should be especially well appreciated here at Pittcon, you would need an instrument such as this. This is an open-air, sit-down MRI machine from a hospital in New Jersey. And the reason you'd want an instrument like this to do single chemist spectroscopy is that whether you want to admit it or not, this is your natural conformation. In fact, you're all in this conformation right now. I get laughter from the single molecule crowd on that. And it would be nice to find an analogy to this for looking at a single molecule. One common approach, and WE introduced this earlier, for looking at single molecules in solution is to take a laser and a lens, a very powerful lens, a microscope objective, and from a very tightly focused excitation spot in solution, and one can sort of wait for molecules to kind of haphazardly diffuse through them. The problem with this approach is that you only get a couple milliseconds of viewing time, and it's passing through an inhomogeneous excitation volume. It would be a bit like having a device like this, but rather than sitting in it, you would sort of take a running start and hurl your body through it. And that's clearly less than ideal. A more common approach for looking at single molecules is to immobilize them in some way. This might mean dispersing them on a surface or covalently attaching them to a surface. And this also works in the sense that one can get arbitrarily long viewing times. But one has every reason to at least be suspicious that one might be altering the conformation in some way, that one might be causing some kind of unnatural conformation. Right? And I do mean be suspicious. In some cases, with a lot of rigorous control experiments, you can show that whatever process you're interested in is not being affected by immobilization. but that story doesn't always have happy ending. It would be nice if we didn't have to worry about it. And so a number of groups have endeavored to fill this niche. The Murner lab and hopefully soon the Goldsmith lab are filling it with a device called the ABEL Trap, or the Anti-Brownian ELectrokinetic trap. What the ABEL Trap does is it uses electrokinetic forces to compensate for and cancel out Brownian motion. And so when the molecule diffuses to the left, we give it a kickback right. When it diffuses to the right, we give it a kickback left. And in this way, we can actually, again, compensate for Brownian motion, at least over some length scales and time scales. You might ask how you know what direction to apply the feedback. In the first generation of the ABEL Trap, we would simply image this whole region using wide field excitation, and I would know the molecule's over there, and therefore I would know I would need a force vector in this direction to bring it back to the center. And that works for large, lumbering molecules. But for fast molecules, by the time you download your 512 by 512 pixels, have your computer calculate the force vector, your molecule's gone and never coming back. And so in the second generation of the ABEL Trap, we replaced that wide field excitation with a single spot, but a spot that actually rotates as a function of time, and then phase locked to that spot is kind of a would-be or a hypothetical force vector, such that when a molecule comes in, right on cue, at the instant that it overlaps with that excitation spot, it's excited, it fluoresces, and at the instant that that fluorescence emission is detected, that hypothetical force vector is essentially instantly gated into a real force vector. And because the spot is way to the left and a little bit high, I know I need a big force in this direction and a little force in that direction that gets applied by two pairs of orthogonal electrodes. All right, and then we repeat this process about 40,000 times a second, and that way cancel out Brownian motion. So what are these kicks? Well, everyone knows that if you take a charged object and you put it in an electric field, you'll induce a motion in that object. This is the well-known electrophoretic force. But this is a little bit unfortunate because the molecules that we're interested in studying, we tend to study them pretty close to their isoelectric point, which means their net charge is relatively small. So this isn't really going to cut it. Luckily, at the dimensions of a microfluidic device, another force becomes important. So we make our device out of silica. And so the surface of our silica is a whole bunch of SiOH bonds that at these pHs are deprotonated. And so we get a layer of negative charges, and then counterbalancing those negative charges is our Debye layer, a layer of positive charges. When we apply a field now, the negative charges feel it, but they're not going anywhere. They're stuck to the surface. The positive charges also feel it, and they are going to move. And because we're in some solution of finite viscosity, that solution is going to drag anything with it, including any neutral objects in solution that we're interested in studying. So that's pretty convenient. So we can combine our rotating spot position estimation system with our electroosmotic actuation system and use it to make movies like this. These are, again, single proteins fluorescently labeled, contained at the center of this image without any immobilization for multiple seconds. The genesis of the ABEL Trap is reported principally in these two papers here. Adam's now a professor at Harvard. What I'll be telling you about are my adventures applying the ABEL Trap and about silly pictures in the Murner lab at the end. So the first actor in my story is a photosynthetic antenna protein called Allophycocyanin, or APC. APC is a trimer where each monomer contains two pairs of these phycocyanobillin chromophores. Right? The electronic properties of APC are defined by a collection of both strong intrapair and weak interpair interactions between these PCB chromophores. And it really endows APC with a very rich photophysics. So the first thing we did was we put APC into the ABEL Trap, and here's what happened. At time 0, my molecules of APC are diffusing randomly. Eventually, when they get close to the center, they overlap with that rotating spot, and they're immediately swept up into the trap, where they then experience a spatially flat excitation, hence we get a plateau. But we don't get one plateau, we get multiple plateaus, we get dynamics, but it's real, honest-to-God dynamics, not a molecule diffusing in and out of an inhomogeneous excitation spot. All right, so what do we see? We see many plateaus. All right? We can then highlight those plateaus using a change point finding algorithm described by the guy who's giving the talk after me. And that's what I'm showing in blue. We can do one more step also. Because we're using a pulsed excitation and we're doing our recording by time-stamping every single photon in the process of time-correlated single photon counting, we can extract lifetimes and assign a fluorescence lifetime for each one of these intervals. Right now, so what do we see? In some cases, the intensity and the lifetime track each other. as in this case. In other cases, they are anti-correlated. Here, the intensity is dropped, the lifetime is actually going up. And still in other cases, there's no correlation. Here, the intensity is dropping precipitously, but the lifetime is staying more or less constant. So we have a range of different photochemical phenomenon to explain, and this is sort of the fun part of being a physical chemist, I think, is trying to explain all this stuff. Okay, so let's ask some simple questions first. How many different intensity levels are there per molecule? We can apply an agglomerative clustering algorithm and answer that question, and we see up to at least 4 or 5 unique intensity levels per molecule, maybe even 6. Well, that's interesting. It turns out we're not the first group to ask this questions. 2 other groups have done a non-solution phase single molecule experiment and also asked how many individual steps. One group saw up to 3 unique steps. Another group, looking at the same molecules of APC, literally from the same commercial vendor, saw up to 6 photobleaching steps. Well, that's interesting. We have kind of a mystery here. And what I think the critical difference is between these 2 studies is actually how the molecules were immobilized. And so on top, the molecules were immobilized non-specifically on a glass slide or dispersed in agarose. And on this bottom slide, as well as on this bottom slide, they were immobilized non-specifically in a thin film of polyvinyl alcohol. And so this first result of the study is that for APC at least, the method of immobilization actually makes a huge difference. And it seems that immobilization on a glass slide causes APC to exhibit dynamics that are qualitatively different from its solution phase dynamics, but we are only able to see that because we were able to do the solution phase measurement. So that's pretty exciting. Okay, what about the lifetimes? So on the right, I've taken all the lifetimes that I've measured. I made a big histogram. Single molecule people love to make big histograms. In that PVA group, the 6-step photobleaching group, they made that same histogram. And they look pretty similar. But the biggest difference that I see between these 2 is that in the immobilized case, the histogram's a lot fatter. And I think this makes sense when you take a population of single molecules and you immobilize them in a polymer. Each molecule is going to experience a subtly different microenvironment, which will cause it to adopt a subtly different conformation, which will cause it to give you subtly different photophysics. And so what we have here is sort of a smoking gun for what a solution phase measurement can give you by substantially reducing that inhomogeneous broadening. Okay, what about dynamics? What about correlations between lifetime and intensity? Right? So I can take every interval for every molecule that I see and characterize those intervals by an average intensity and a lifetime. And that's what I'm plotting here. Right, and there's some structure here, not as much as I was hoping to find when I first did this experiment. But then I realized, one more detail. So there's not much fine structure, but almost every molecule that enters the trap enters it in this tight grouping of points here with high intensity and high lifetime, but only after repeated photoexcitation do we start accessing this broad analog distribution of lifetimes and intensities. Well, that's interesting. Right? I then realized that I'm not so interested in these points themselves. I'm interested in the transitions between those points. And so as every molecule undergoes its business in the trap, as the intensity rises and falls, as the lifetime goes up and down, it's traversing some trajectory in this intensity lifetime space. And I'm more interested in these jumps, which are just vectors in this intensity lifetime space. And because they're vectors, I can move them all to a common origin. I can add in the data from 1,000 other molecules probed one at a time in solution to make this plot, which my former office mate used to call my Supernova Plot. And what you have here is a nice representation of all of the different photodynamics that we can see. In most cases, we see a drop in intensity coming with a drop in lifetime. So drop in intensity, drop in lifetime, or increase in intensity, increase in lifetime. But you also see population in all these other quadrants, including changes of lifetime at constant intensity, which was very weird and unexpected. Right, so how do we start explaining this? Well, we can start out trying to relate the intensity to the observed fluorescence lifetime, and we can do that through the quantum yield. And what's typically assumed is that it's only the quenching rate, the non-radiative rate that changes, which would only give you population in these quadrants. And it'll give you sort of a narrow distribution of slopes as well. In fact, in order to get population in all these quadrants, especially along the axes, you need to invoke a fluctuating radiative and non-radiative rate. And again, that was very unexpected. So why might that be happening? And how can we relate this to this photo-induced effect that we're seeing? And I think what we're seeing is evidence of light-induced conformations. We repeatedly excite the protein. We go into some dark state that's possibly charged. This induces conformational changes. And what we're seeing are the effect of these conformational changes. They alter the quenching rate and the radiative rate. This gives us a distribution of correlations between intensity and lifetime, right, which is exactly what we see. So everything's more or less consistent. Okay, so all those were photo-induced changes. All right, we would like to be able to study intrinsic dynamics of a molecule in the solution phase using the ABEL Trap. And so we sort of focused on enzymes being a particularly dynamic type of biomolecules. And we certainly were in the first group to look at enzymes one molecule at a time. And I think the most conceptually simple way of looking at the action of a single enzyme is to study the formation of a fluorescent product from a non-fluorescent substrate, and every time you have a successful reaction, you get a burst of fluorescence. And one of the beautiful things that was seen in these types of experiments was that the rate constants of individual enzymes actually fluctuated as a function of time. Now there's a problem. There's two problems with this. One, typically these enzymes that are themselves immobilized on a substrate, and so we'd like to see if these dynamics would also occur in solution. The second problem is that you're only seeing the last step here. It's like having a really rich novel, but only being able to read the last couple of pages. There's a lot of dynamics happening before that final formation of bonds that gives you a fluorescent species, and these types of techniques are blind to that. And so a particularly elegant solution was recently published by the groups of Thijs Aartsma and Gerard Canters at the University of Leiden, while looking at an enzyme called Nitrite Reductase, or NIR. NIR catalyzes the one electron reduction of nitrite to nitric oxide. The enzyme itself is a trimer. It looks a lot like APC, but it's not APC. Take my word for it. Each catalytically competent monomer has two different copper centers, a so-called type 1 copper center and type 2 copper center. And I'm going to quickly run through the mechanism of this enzyme. So at time 0, we have both copper centers oxidized. Eventually, a sacrificial electron donor in solution reduces the type 1 copper center. An intramolecular electron transfer event sends the electron from the type 1 copper center to the type 2 copper center. Excuse me. This is where the substrate binds. We get reduction. We're back to where we started from. And the neat thing about this enzyme is that the absorption spectrum is exquisitely sensitive to the redox state of specifically the type 1 copper center. And so when that copper center is oxidized, we see a broad absorption in the visible that gives these enzymes their characteristic color. But when that same copper center is reduced, that absorption goes away. And so what this group did was they attached a fluorophore very close to that type 1 copper center. And in these cases, the emission from that fluorophore is severely quenched. But in this case, it's unhindered. You have a bright, happy chromophore. All right? So what they did was they turned that fluorophore into a fluorescent indicator of the redox state of that type 1 copper. All right? And they were doing some single molecule measurements on surfaces. And so I was interested to do these experiments in solution. And so I emailed Professor Canters and I said, we have this great tool called the ABEL Trap. Do you think you can send me some protein? And he said, I'll do you one better. I'll send you some protein and a postdoc to tell you how to use it. And I hope all my collaborations start out that well. So Leandro arrived at Stanford. We worked together for a week, and then I spent the next bunch of months actually learning how to do this experiment properly. So here's what we saw. All right, we put these NIR molecules into the ABEL Trap, and again we see fluctuations. But we don't see fluctuations from several unique states. What we see are fluctuations between basically two plateaus, a high state, a low state, both distinguishable from background. We can take the raw data, the raw timestamp data, again apply a change point finding algorithm, but this time as sort of a smart low-pass filter. And that's what I'm showing here. We can then use just a thresholding algorithm to then assign states into either being in the lower state or an upper state. And every time you see a shift between that upper state and lower state, or vice versa, again, you're seeing evidence of a single copper atom changing its redox state inside of an enzyme in solution, which I still think is pretty exciting. Okay, so we can take this data. Okay, so first thing we can do is we can make, again, single molecule people love big histograms. We can make a histogram of all the different intensity levels that we see, and now we can do a good sense check. If we're looking at an enzyme, we'd like the behavior of that enzyme to be in some way affected by the amount of substrate we put in solution. And here our sense check succeeds. As we start adding more and more or higher and higher concentration of substrate, we start growing in a higher equilibrium fraction of that lower intensity peak. So great, we're We're not looking at something totally artifactual. Right? We can then go back to our raw data and start looking at the amount of time we spend in the lower state versus the upper state. Here I'm plotting the dwell times in the upper state, and see how the distribution of dwell times is impacted by the substrate concentration. And what I see is that I start out at low concentrations with sort of a gradual decay, and as I increase my concentration, my decay sharpens up considerably. And I'd like to be able to develop a means to quantitatively model my changes of dwell time distribution, and to do that I'm going to start with a proposed kinetic scheme. So focus on the two boxes here. The boxes represent the oxidation state of the two copper atoms. And so here they're both oxidized after reduction via a sacrificial donor in solution. My type 1 copper center becomes reduced. This is the emissive state. Electron transfer, I shift my electron. Now it's not emissive again. Chemistry links up to the other side. I can take this scheme, and I can start out by writing the differential rate law if I want to start deriving these distributions. Right, but the really nice thing about doing this in a single molecule experiment is that you're looking at a digital system. Right? I have three terms here, one depleting that state here, and two populating it. But again, it's digital. It's either in that state or it's not in that state, which means I don't have to worry about all the terms populating it. I only have to worry about the terms depopulating it. I can then integrate up to my integral rate law, then take one more derivative to get my expected dwell time distribution. In this case, I luck out, and it's a simple exponential. And I can then fit these guys to extract 5 different values of K23, my rate of intramolecular electron transfer. And I'll plot those values here, and it actually makes a big difference. When you start increasing substrate concentration, you get over a factor of 2 increase of that electron transfer rate. Right, so it turns out that we weren't the first person to ask, how does that rate change? Right? One group of experiments using pulse radiolysis saw a substantial decrease of electron transfer rate when they added a bunch of substrate. Right? Another bunch of groups using magnetic resonance and using X-ray absorption spectroscopy, well, they saw evidence that the delta G of electron transfer should increase upon binding the substrate. And since you're still in the Marcus normal region, that should give you an increase of electron transfer rate, not a decrease. Right, well, that's frustrating. Another bunch of experiments looking at thin films of NIR on an electrode, well, they saw in some cases it increased, and in other regimes it decreased. Right, well, that's also sort of unsettling. Right? All of these experiments are done in single crystals at low temperature, so clearly very far from turnover conditions, which is where you really want to be studying your enzyme. There was no substrate in these experiments. I'm sorry, there was no reductant in these experiments, all right, only substrate. So also not turnover conditions. These experiments were on a surface. They were done under turnover conditions, but all of these values, like these rate constants, including the electron transfer rate, were all a function of 11 different parameters. Right? You couldn't get that value directly. By doing the measurement in solution, one molecule at a time, we pull out this number directly and say pretty clearly the electron transfer rate increases as a function of substrate concentration. So that's pretty gratifying. Okay, so why? And this ultimately, we asked this question and then almost regretted asking it after we asked it. So here's sort of a zoom in of my type 1 copper center and type 2 copper center. All right, so why would the electron transfer rate change as a function of substrate concentration? Well, there's been some suggestion that when you bind the substrate to that type 2 copper center, you change the energetics of that electron transfer, so you change the delta G term in your Marcus equation. You might also induce conformational changes, which might alter the electronic coupling between your two states, which might change the V squared term in your Marcus equation. Right? But either way, now it seems to matter a whole lot whether I have electron transfer and then binding versus binding and then electron transfer, which means my model just became obsolete. Right? In this model, I have electron transfer, then binding. This model is not flexible enough to model what I need to do. And so I then move on. I'm going to call it a simpler model, even though it doesn't look simpler. Here, I explicitly treat substrate binding. So I added a third box, which is either filled with an S or empty. And here I have 2 channels. I have electron transfer and then substrate binding, or substrate binding and then electron transfer. And I'm calling it a simpler model because there's 10 free parameters in this case. Whereas in the previous case, with 5 values of K32 and 5 values of K23, my forward electron transfer rate, and 5 values of K32, my back electron transfer rate, I actually get 12 free parameters. So That's why I'm calling it simpler. In every other way, it's much more complicated. All right, so I can go back to my data. And again, I look at my dwell time distributions. Here I'm showing the upper state and the lower state. Again, as I increase substrate concentration, that distribution tightens up. Here, as we go look at the dwell time in the lower state, in the oxidized state, I go from sort of a sharp decay to a more gradual decay. So I get opposite trends in my dwell times in the upper state and my dwell times in the lower state. Okay, I can go through the same rigmarole as before. I again write down my differential rate law, but again, I have two bright states, so I have to do it twice. I again lose all my terms that populate this state, and only look at the ones that depopulate it. Then I integrate up, and I won't show you the result of that. It's several slides long. I also have to worry, and then I take another derivative to get my dwell time distribution. At this point, though, I also have to worry about multiple ways of populating my bright state manifold. You can come in through here, you can come in through here, you can come in through here. That also enters into the analysis. I do the same treatment for the lower state as well, which ends up being even more complicated because I have three states. And now I start worrying about constraining my parameters. Right? This is always an issue when you have these big multi-parameter fits. So I need more data. And so what I go to is I also look at the equilibrium populations. If I sum up all the time my molecules spend in the on state and all the time they spend in the off state, I can express that ratio as a function of all of these same parameters in my kinetic scheme. I can then do and I'm showing that here, I can then do a massive global fit to extract all of these parameters simultaneously. And I'm showing the fits here to all of this data. Okay, so here's my list of numbers, all right? So how does this jive with the data I showed before with the electron transfer rate changing? I'll call your attention to Kc and Kd. This is the forward electron transfer rate without substrate and the forward electron transfer rate with substrate. And I get about a factor of 2 difference between them, which is consistent with what I was showing here. Here I didn't allow for 2 pathways. I basically have an interpolated value between them. So this is all still consistent. Again, I see very clearly a model consistent with substrate binding giving me an increase in electron transfer rate. Okay, now whenever someone tells you they just did a 10-parameter fit, you should be extremely skeptical. That's just good advice to live by. And so we endeavored to actually assess how good of a job we could do in estimating these parameters. And so what we did was we calculated the expected Fisher information for all of the different parameters we can measure, and we used that Fisher information to then give us the Kramer-Rao bound. This is essentially the best you can do in estimating your parameters, assuming you've actually included all of your noise properly. So we're never going to do better than the Kramer-Rao bound. Now, if we go back to my table here, what we find is that for about half of the parameters, we do a great job. And the other half of the parameters, we do a decently lousy job, unfortunately. And the identity of those parameters isn't, what we do a good job isn't that surprising. If we switch between manifolds, we get a clear on-state to off-state switch, or vice versa, we do a pretty good job. But these intrastate shifts are a bit harder to estimate, so we don't do as good of a job with them. We can take all these parameters, we can take all these parameters and then propagate population in these states as a function of substrate concentration. And what we see is that in regimes of low substrate concentrations, we proceed presumably by this lower path, by having electron transfer, then substrate binding. And at higher concentrations, we proceed selectively via the upper path, substrate binding, and then electron transfer. And at intermediate concentrations, we see evidence of both pathways being active. So that's more or less logical and consistent. Right. With that, I'll summarize my 2 topics. We can trap APC and nitrite reductase in solution, and that's great. The APC does neat stuff, which is even better. And when we analyze that neat stuff, we come to a conclusion, or we find a model that includes light-induced conformational changes, and we think we need that model in order to explain the observed data. We can see redox shifts of single copper sites in VNIR, and use that via multi-parameter fitting algorithm to extract many of the parameters of that kinetic scheme, again, under turnover conditions. Right? If you wanted to do a bulk experiment, you'd have to find one set of conditions where one parameter becomes rate limiting, so you measure it, or then you have to find another set of conditions where another parameter becomes rate limiting, so you can measure that parameter, and hope nothing else changes. But by doing the single molecule experiment, again, we can extract a whole bunch of those under turnover conditions, and that's pretty exciting. So with that, I'll thank first my collaborators in this nitrite reductase project, especially Leandro. I want to thank a bunch of people, both current and former Myrna labs. I'll thank WE really quickly here. We're going to thank him more in a minute. The APC story was published a year ago. The Nitrite Reductase story was just published. I know everyone thinks that life as a first-year assistant professor is all sleeping late and taking it easy. But we've actually been at least a little bit productive in my first 6 months there. We've started looking at dynamics of proteins during translation, dynamics of nascent peptides still stuck to the ribosome. This is in collaboration with Silvia Cavagnetto's group in my department. And at the moment, we're still in the hurling your body regime. But we can actually see single chromophores attached to ribosomes, and the hope is to someday actually watch conformational dynamics evolve by holding onto a ribosome in the ABEL trap. That'd be pretty exciting. We're also doing something that has nothing to do with fluorescence at all. We're interested in developing ultra-high Q optical microcavities as a means to measure dynamics of single molecules. This is what we're trying to make. This is the work from Kerry Vahala's group at Caltech. This is where we've gotten. All right, so we're actually pretty close. The critical step that's missing to go from structures that are sort of rough like this to structures that are smooth like this is a CO2 laser-induced reflow step. According to FedEx tracking, our CO2 laser arrived earlier this morning, which is really exciting. So hopefully we're not too far away from that. And we have a group. We talked about label makers earlier. Morthu actually broke our label maker like a few weeks in, which was really just disheartening. But then Kevin fixed it, so it was all okay. So we didn't, our organization didn't suffer. And we're building a group, and it's exciting. Okay, so here's the silly picture part. So it's tradition in the Myrna lab when something really amazing happens. It could be someone's defense. It could be the publication of a particularly exciting bit of data. We pop some champagne, okay? Can anyone hazard a guess as to why we're all wearing headgear in these pictures? Does anyone have any idea? Safety first. Okay, we follow a very tightly, a very positive example set by WE. And we pop the champagne. But okay, any group can pop champagne when something nice happens. Here's what's unique about the Myrna lab. All right, so after we pop champagne, you can see me sort of doing it here, aiming down the hallway. Someone comes in and then measures exactly where the cork landed. Okay, you can see WE giving me advice here. How is by now he's technically an honorary member of the Myrna lab. I think the only reason that there's not pictures of him doing this is that he doesn't drink champagne. That was the only reason I could think of. So, here's Mike marking it down, and here's the nice part about all this, right? When you or I come to work, we walk through a hallway, we get to our office, and then we get there. When WE walks through a hallway, he's surrounded by tangible evidence of all the successes of his students as he gets to his office. Now, WE he's too modest to be thinking about that when he walks down the hall. He's too focused on getting the next exciting scientific result. But I hope that someday, once in a while, he actually does think about all the great science going on in his lab, done by all these wonderful people. And I hope he thinks about it, relatively often, once a week at least. And it's just great that he has this tangible reminder. It's also led to a fascination in the Myrna lab with just bizarre headgear. This is Anika, who did the bow tie work earlier. And it was a wonderful place. And thank you for your time.
It will be by Ha Yang from Princeton University.